All right. Welcome to the old school way of doing these. I used when I first started teaching my physics sport class online. This is the way this is the way I did it. I'd make a little like 7 or 8 minute vignette. I'm going to make two of them. Here we're going to do two problems because I was realizing today when I was going through, and I really do enjoy going into your questions on the homework. So keep it going. Some of you might run the gamut of asking too many on one question, but that's all right. And Anyway, because I realized all of a sudden, I was thinking you're not doing any worse than any other class. In fact, with all the things going on, with everything that's going on, you're doing quite well. And then I realized you can't come to an office hours. And I used to have 2 hours of office hours, like I'd have them on Tuesdays and Thursdays from like 1 to 2 or something like that. And you could schedule, or if that didn't fit your schedule, you could schedule one and come in. And we don't have that option. I mean, we could schedule a Zoom, but that's still, I mean, it's fine, and it would be okay. We could share, or you could watch my ladybug or whatever. But we can't exchange ideas. So I thought, well, what's the next best thing? Just go ahead and pick a problem and work it. And then what you have to do though is you have to um, work it following my steps, and then put my stuff away and come back the next day and try and do it all on your own. See if you can do it on your own, because it is like learning a speech. It's like learning music. It's like because the problem I have is I see the two big ideas that they're trying to get across, which is basically Newton's second, the three laws of motion. Um, and you all see these hundreds of little things going on, like this coefficient of friction stuff, and some of it's kinetic, and one of it's static, and the static is bigger than the kinetic, and what the hell's with this tension thing going on? So I let's just do two problems. So this first video is going to be problem for homework number 9, because I'm getting some questions on it. And when we go through these, it'll also offer insights into the one where they're having the different normal forces. Okay, because remember, the normal force is just a force that's going up. It's the perpendicular force that's opposing all the other forces that are smashing it down. Okay, and if it's at an angle, if the thing's at an angle, then it's the cosine of that angle is what the normal force is that's perpendicular to it. All right, unless there's something else holding it up here, or pulling it. You can get into all kinds of neat engineering type problems that we're not going to do. That just all they do is they just incorporate a bunch of things. We just put a bunch of stuff together. On the basic ideas, and that's one of the problems we're running into. It's like the quote on my email. We instructors see 4 or 5 big ideas, and you guys see 400 or 500 equations. And that's kind of the nature of the beast. All right, let me write down what we're going to do here. Then we'll turn on the ladybug. In fact, I'm going to turn it on now so that we can see it. Make sure that it comes up. There it is. Okay, so make her big, and then we'll come back here and we will look at, sorry, I'm driving you crazy. All right, let's look at this. A donkey is harnessed to a mass of 206 kilograms, and I'm going to draw the picture here in a second. I'm not going to draw the donkey, and it's exerting a force of 1,250. The donkey must exert a force. He's got to exert a 1,250 Newton force at an angle of 34.3 degrees above the horizontal in order to get the sled moving. Okay, he's losing now. If he got down even and pulled with 1,250, it would really start to accelerate. All right. But he's got to pull up at an angle, so he's losing some of that pull and taking it up at an angle. All right, so theta is equal to 34.3 degrees. Mass of the crate is 206 kilograms, and we'll get all that here in a second. And donkeys in red too. I guess some of you had horse. And the force is at 1250 newtons. So this is a lot like one of those other problems also. Okay? And we want to find out, calculate the normal force, and then find the coefficient of static friction. And then we'll look at the last problem. I'll click it again, and then we'll look at the last problem. All right, so here's the deal. It's getting pulled up this way at this angle is 34.3 degrees. Okay? All right, now we're going to break that down into its components. It's got a force going this way. That's the f of x, and it's got a force in the y direction going this way. F of x is equal to 1250 cosine of 34.3, and f of y is equal to 1250, it's positive, times the sine of 34.3. Make sure your calculator is in degrees and not radians. I think one of your fellow classmates was thrown off by that. Now, next thing, there's a static frictional force going this way, and we're getting the max. We're going to find out what that maximum static frictional force, because anytime you pull on something and it doesn't move, there's a static frictional force opposing the motion. Okay, until you pull, then it breaks free, and then it goes loose. Then it breaks loose, and then the kinetic frictional force is always less than the static frictional force. All right, so we're going to calculate that static frictional force. There's two other forces missing here. There's the normal force that we're going to have to calculate, and then there is mg. Okay, so we've got three forces going in the y direction and two forces going in the x direction. We break them down into their components and look at them individually. So I got the sum of my forces in the y direction are equal to 0 because it is not accelerating. Static friction means it's not moving. Kinetic friction means we're getting it to move. Okay, so let's just go around the horn and let's just take a look at the forces here. So we've got N, the normal force, plus we've got Fy minus mg. Hey, cool beans. I got numbers for this and this. Okay, so I'm going to say mg minus Fy is equal to N. What did I do? I brought all these over to the other side. When I brought this to this side of the equation, it became negative. When I brought this side, it became positive. And so I've got 202 times 9.8 minus 1250 times the sine of 34.3. That's the other thing. You do all your calculations at the very end. You get it all set up. I mean, when you start getting in real upper level physics, when you get down to here, you're done. All right, because plugging in the number, But we want to see how we did here. So we got 202 times 9.8 minus 1250 times. I also think I owe you guys one too from Monday's lecture. God, that is a flusher. All right, so sine of 34.3, boom, 1275. So the normal force here is equal to 1275 newtons. Yep. All right. Now, I think the next thing that they asked, how come they got 1310? Oh, I did 200. Again, this is supposed to be 206 newtons. 206. You all are screaming and going, no, it's not. It's 206. So let me redo it. So if I go ahead and put in redo my entry and redo the 202 instead of make it 206. Yes, I got 1314. Okay, and they're going 3 sig figs. So I'm going to put in my 1314 here. I'm going to change it here to 1314 because it's 206 newtons. 1314 newtons. See, I didn't practice this. I was like, okay, because sometimes you got to get over. Now, notice I've got the answers right here, so I know what I need to come up with. So find the coefficient of static friction between the sled and the ground beneath it. All right, now, where's the static frictional force? Let's take a look at our picture again. Where's the static frictional force? It's over here. It's in the x direction. Is this thing with static frictional force, is this thing accelerating or being pulled? No, it is not. So let's go ahead and take the sum of the forces in the x direction are equal to 0 because it's not accelerating. And what do we have? We have f of s, and I'm going to leave it as f of s. Okay. Now it said it wanted the magnitude of it, so we'll give, well, we're getting the coefficient of the kinetic frictional force is minus or plus f of x plus 1250 times the, yeah, okay, 12, excuse me, 1250 times the cosine of 34.3, right? And so when I bring that over, I get negative 1250 times the cosine of 34.3 is equal to my static frictional force. That's the vector sum of it. Okay, but we're going to go ahead and take the magnitude of it is equal to 1250 times the cosine of 34.3, and that's equal to 1032. They probably went with 1030 newtons. Okay, now you're going, well, wait a minute, that's not what they had. No, they wanted the coefficient of kinetic friction. They wanted mu of k. What's mu of k equal? Well, we know that f of s is equal to mu of k times the normal force. Did we calculate the normal force? Yes, we did. We got 1314 newtons. Right here's the normal force. Okay, so if I take f of s, which I got is 1032, divided by the normal force, which is 1314. This is f of s divided by the normal force. Okay, 1032 divided by 1314 is equal to 0.786. Notice no units because this is newtons and this is newtons. So there's no units there. All right. Now, what is part D? What else do we have to do here? What other torture did? Okay, so we got the 0.786. I got that right on the nose. All right, so now find the static frictional force when the donkey is exerting a force of 625 newtons. This isn't hard. This isn't hard because when he's exerting a force of 625 newtons on the sled at the same angle. Okay, so he's halved. He has halved the he's halved the 1250 here. I didn't notice that before. So because I've done these 1,000 times, and we got that 1032 was, looky here, when it was being pulled at 1314 newtons, okay, I got 1032 for the static frictional force. Now, what are they doing? Or that was the normal force. But when it was being pulled at 1250, when it was being pulled at 1250 right here, I got 1032. Now what happens if I'm going to pull, notice it's linear, so if I'm going to pull with half of that, this I should be able to divide the 1032 divided by 2 and get the right answer. But let's just go ahead and walk the dog anyway. All right, on part D, in case, because that's one of those things when you teach this stuff for a living, that's one of the things you notice. All right, as long as you're not overthinking, where I get into trouble. Okay, so let's take a look at this. Now remember, the coefficient of static friction does not change. That's what we calculated. But that's going to keep it from moving. There's a certain point where it will start to accelerate, where we will get this thing to accelerate, and there is a maximum force that will just get it to move. But anyway, so here we go. So now we're going to say the force in the force exerted by the horse is now 625 newtons. No longer is it the 1250. So the force in the x direction is going to be 625. They said it's at the same angle times the cosine of 34.3. Okay, and so 625 times the cosine of 34.3 is equal to 516. 516 newtons, and we know that the sum of the forces in the x direction is equal to 0, which is equal to the static frictional force minus or plus the 516 newtons. So the static frictional force, the actual magnitude and direction of it, is negative 516 newtons, but they wanted just they just wanted the magnitude, so you'd put in the 516. And I know what you're saying. Well, gosh, that sure looked easy when you did it. I followed everything here perfectly. Yes, you did. You know why? Because you're smart. And secondly, you just need to practice. That's all. All right, let's do one more, but not on this. We're going to, I like to keep it around 12 minutes. Otherwise, I go nuts trying to record these.